Hi, welcome. Today we're going to talk about pH regulation of the stomach, and it is important that we understand that pH regulation can be done in several different ways. But before we do that, we need to understand a little bit about how the stomach works and what is its normal pH. So pH in the stomach is normally caused or determined by the concentration of the gastric acids, and that's going to be mostly composed of hydrochloric acid, HCl. And because of that, the pH there is going to be approximately between one pH unit and 2. So that's normal pH. We need that acidic medium, that low pH, in order for the digestive enzymes to be able to do their work properly. All right, one of the important things that they need to do is that they have to be in the right configuration in order to be able to break all of those bonds between peptides, between fats, or other food goods that we're going to be digesting in our stomach. The second reason that we need to have a low pH is in order to keep pathogenic bacteria from actually multiplying too readily. It's a nice thing that most bacteria will not tolerate the highly acidic medium that is present in the stomach. Their cell membranes, the cell walls and the cell membranes will lyse, all right? And so this actually keeps them in check, all right? Now, the stomach itself can withstand the highly acidic medium because there is a nice thick layer of mucus. We don't normally like to think about mucus, but we actually want to have this mucus layer in our stomach. By the way, our stomachs are up here, all right? Not very low. They're very rich, really right behind our heart. That's why it's called heartburn when you have dyspepsia. We'll talk a little bit about that in just a moment, all right? But the proteins that make up the lining of the stomach and that mucus layer protected so they can withstand the acidic medium. So let's look at how that looks a little bit, all right? So here you have a nice little picture of the stomach, all right? I wish I had chosen one where you can actually see the heart, but in any case, or the rest of the body. But it's here in this pit where we're going to be producing all of the acid. And so we have the parietal cells right over here that are actually going to be emitting or producing glands that are going to be producing the gastric juices, mostly hydrochloric acid. All right. They also will be producing the mucus layer that actually protects that tissue from being damaged because of the acid. All right. Now, even though this is all well and good, the reality is that we always are going to have the possibility of having too much acid, and that acid causes irritation, all right, because of overproduction of the gastric juices, or because the mucous membrane or the mucus layer has been broken down. This can be just naturally, or it could be because you have been taking some type of medicine, some type of a drug that can actually cause this to break down, all right? So we can get to have a couple of different conditions. Indigestion, or otherwise known as dyspepsia, is just a mild problem. Heartburn is when we're going to get some of the acid flowing back up to this esophagus. And let me just show you again. All right, our esophagus is the top part of the stomach. All right, and it will just be right behind our heart, and that's why when we have pain there and that acid goes there, where there are no mucus layers, where the proteins are not designed to withstand the acidic medium, we are going to have some damage, some irritation, and that's why it hurts. All right. And the final issue that we can have are peptic ulcers. Peptic ulcers are very particular. We're going to talk about them in just a moment, but this is a severe irritation of the lining of the stomach. All right. We're really going there, and it can cause bleeding, so they can become very dangerous. All right, so we'll come back to that. But the first thing that we want to see then is how can we kind of help ourselves when we have indigestion, when we have heartburn. All right, and so the most common way to do it is to use regular antacids. Now, those are used to treat dyspepsia, all right, the small amount of excess production of acid. This is something that you would use if this is not a recurrent problem or a chronic problem. This is just more of like being just a couple of times, all right? Now, what are the three components? And sorry, let me just talk about this image here. Here you can have, our esophagus normally has a sphincter that closes the acid and does not allow the esophagus to actually get some acid. When we have problems with dyspepsia, with too much acid production, etc., etc., the acid can flow back up because the sphincter allows for that acid to flow back up through your throat to your esophagus, and that's what we're going to cause that discomfort. All right. Now, antacids consist of three main components. The most important one is going to be a weak base in order to neutralize the acid, the hydrochloric acid that is in your stomach. Now, the most common components are going to be sodium bicarbonate or sodium hydrogen carbonate, calcium carbonate, aluminum hydroxide, or magnesium hydroxide. All of these are weak bases. They do not have a strongly basic component. Why won't we use a strong base? Because obviously a strong base would also cause damage, because being strong, it can cause irritation to all of those membranes on our throat and our stomach. So they would actually cause more trouble than what they would be fixing. All right. Neutralization can happen with a strong base or a weak base. So we use a weak base because it is milder. All right. Now, you must be able to write balanced neutralization reactions for all of these. And it's important that you remember, if we have a carbonate, one of the things that we're going to produce is carbon dioxide. If we have hydroxides, all we're going to produce is the salt, the chloride salt, and some water. Okay, so look at those equations. Make sure that you're able to write those down, that you should be able to balance them. Okay, because this is a kind of question that they can ask you, whether it's just only to write that or to calculate a little stoichiometry question, which we will be doing in just a moment based on that. Okay, so our antacid component number one is to have that weak base in order to neutralize this. Okay, so in each case, the acid is going to be reacting with the components, either the carbonate or with the hydroxide, and therefore be neutralized. Make some water, all right, and in the case again of carbon dioxide, making some of the carbonate, making some carbon dioxide. The second component that we have in an antacid is an antifoaming agent, all right? And the antifoaming agent, is something that is very obvious, or like kind of makes sense. Most of the antacids are going to produce some gas, all right? Namely carbon dioxide. And so you do not want to have that bloating, because of course that pressure can push some acid up and actually make your heartburn worse. All right. So these the antifoaming agents just kind of reduce bloating, it reduces flatulence. Okay, they trap the gases. Dimethicone is the most common antacid that you have in things like Maalox or Pepto-Bismol or anything like that. They contain this. The third component are called alginates. All right. And basically they're coating agents. They allow for the weak base to stick to the walls of the stomach, to the walls and the lining of your esophagus, and that way it can actually allow the base to neutralize any acid that is flowing upwards. All right, so it's not just acting at the very bottom of your stomach, but it's acting all over. Okay, so three components. One more time: weak base, antifoaming agent, and alginates. All right, excellent. Now, you can get sometimes questions about how much acid can be neutralized by a particular antacid. All right, and so in order to do that, it is important that we remember we need to use the balanced equations. All right, And so the typical question, this has shown up in several IB exams in the past, all right, is a question such as this one. Determine which antacid would neutralize a greater volume of gastric acid of pH 2. Now, the pH is irrelevant. We do not care what the pH is in order to neutralize it. We only care that we are going to have how much we have. Now, for this, as I told you, we really want to have our balanced equations. It's important that we see sodium hydrogen carbonate can neutralize 1 molecule of hydrogen chloride per mole of, 1 mole of hydrogen chloride per mole of sodium hydrogen carbonate, while calcium carbonate can neutralize 2 molecules of, or 2 moles of hydrogen chloride. So we need to know the number of moles. Now, the good thing is that this particular example here, they've given us some nice easy numbers to work with, all right? Or relatively easy numbers to work with. The molar mass of calcium carbonate is approximately, what is going on? This is not right, there we go, grams per mole. While that of sodium hydrogen carbonate is approximately 84 grams per mole. So we know we're going to have ever so slightly more moles of the sodium hydrogen carbonate. In fact, if you were to calculate that, you would find that you get 0.01 moles of this one and 0.012 moles of the sodium hydrogen carbonate. Well, you say, oh, well, obviously this one, the sodium hydrogen carbonate, is going to have more moles, so it would neutralize more. And that would be incorrect because we need to take into consideration the stoichiometry. The calcium carbonate can neutralize 0.02 moles of hydrogen chloride, of hydrochloric acid, while the sodium bicarbonate will only be able to do 0.012 moles. All right, and so that's very important that we remember that. This part that we're going to be looking at how to control problems of excess acid is going to be, I think I just opened a new page. Let's see. It's going to be how to treat peptic ulcers. All right, which, as I told you, is erosion of the lining because of excess acid. All right, they can be quite painful. All right, and because they can cause internal bleeding, a bleeding ulcer can be very, very, very dangerous. All right, so because you are having, an internal hemorrhage. All right, so there are 2 ways in which we can do this. We can either inhibit the production of gastric acids, which is done by a drug called ranitidine, and ranitidine is an active ingredient present in Zantac. All right, or you can do it by inhibiting the release of the acids. So the stomach still produces the acids, but the cells are not allowed to release that into the gastric cavity, and so they do not get to attack the layers of the acids. This is done by drugs such as omeprazole or esomeprazole, which are present in medicines like Prilosec and Nexium. All right. So let's start with the first one, ranitidine. All right. Now, ranitidine is pretty straightforward, and the structure of ranitidine you can find in your data booklet. All right. It is on table on table 37 on page 39 of your data booklet. All right. Now, how does the ranitidine work? Okay, what it does, all right, to inhibit the production of gastric acid is that it binds to the histamine H2 receptor protein in parietal cells. Yes, you can read it yourself on this screen. But what does that mean? Histamine actually is a chemical messenger that tells these parietal cells to produce acid. If we have ranitidine binding to the histamine H2 receptor, it says, nope, sorry, you cannot activate. All right, it blocks it from activating that receptor. And so because it blocks its action, because it stops it from acting, it is sometimes called an H2 receptor antagonist. All right. Now that H2, careful, has nothing to do with hydrogen. All right. It's not hydrogen. That's hydrogen gas. So it's just the name of that particular receptor is the histamine H2 receptor. Okay. Now here we have the structure of ranitidine. All right. It's a pretty interesting looking molecule. Okay, it's pretty complex, but this molecule actually binds nicely onto this histamine H2 receptor. Okay, now you can see it has some polarities, has some polar areas, but it's not terribly polar. It's still going to be, there's a number of CH2 bonds in there, so we are going to want to make it a little bit more non-polar. Sorry, we're going to make it a little bit more polar in order for it to absorb easily in the stomach. And so we do this by making the hydrochloride salt. As we saw when we were talking about with aspirin or other drugs, polarity is going to be very important in whether you can be absorbed or not. So if we add hydrochloric acid, all right, and the hydrochloric acid tends to add an H to this nitrogen over here, because this nitrogen over here with the two methyl groups has a lone pair, and so we can get an H plus there, and so the entire molecule becomes more positive, and then the chloride is just there to neutralize it. A lot of times you will see this written in this form, in which they don't show you where the H goes, but again, most of the time the H will bind here, make this nitrogen positive, and then your chloride will be there on the side to neutralize the entire salt. That hydrochloride salt is much more soluble, and therefore is more easily absorbed in the stomach. Notice that this particular type of drugs have to actually get into your bloodstream and then act on those receptor cells before they can stop blocking the production of acid. So they take longer time to do this. So a lot of people take antacids first, and they also take this drug for kind of a dual effect. All right. The second method that I was telling you is to inhibit the release of the acid, the gastric juices. The gastric juices get produced, but if we have a drug such as omeprazole, all right, and again, omeprazole is given to you on table 37, but this time on page 38, all right, at the bottom of page 38. Now, omeprazole and esomeprazole are basically the same molecule, all right, but higher level. You will understand this a little bit more. Omeprazole is 1 enantiomer, while esomeprazole is 1 enantiomer, the S enantiomer right here at the top, while omeprazole, just by the name, is the racemic mixtures. It has both hands of the compound. Okay, so it's not as pure, but in a way, it still acts because both of them can act, and it makes it a little bit cheaper to have the racemic mixture, to make the racemic mixture rather than making the enantiomerically pure. All right. Now, the way that omeprazole works is that it inhibits proton pumps. All right, and so protons normally H plus, that's acid. Okay, and so that's what it's doing. Omeprazole stops proton pumps from releasing the acids. All right, this is again in the parietal cells. And how does it work? Let's look at the structure one more time. We can see that it is relatively non-polar. All right, because it's non-polar, it can go through the cell membrane, it can enter the cell membranes, and therefore act inside. Now, inside of the cell, the medium, because it contains acid, is significantly more acidic, and therefore it's going to have a structural change. It's going to become what we call the active metabolite. We'll talk about that in just a second. All right, and will bind to the proton pumps in such way that it deactivates them. Okay, so the active metabolite, all right, is something that happens, and we talked about the active metabolite, for example, in aspirin. Aspirin in the acidic medium stays as aspirin, but when it gets into the basic medium of your small intestine, it breaks down the ester, and it becomes salicylic acid. Codeine as well goes back to becoming morphine, all right? And so it becomes active. Well, omeprazole has this particular active metabolite. It is just a change in its structure due to the medium. Many drugs require active metabolites. Why would we have that? So they can dissolve more easily, they can be more readily absorbed in order to reach the proper target, okay? So those are kind of the common reasons why drugs sometimes require an active metabolite. We have one form that will allow it to be delivered more easily, to protect it from breaking down in a particular medium, and then when it gets to the right place, all right, it becomes its active form, all right? So omeprazole has this particular interesting structure. We have a bond that forms between the nitrogen and this carbon over here. It actually requires the rotation of the molecule that we saw above, but none of this, you're not required to know this particular shape. You just require to know that they have an active metabolite, okay? Now, this happens because of the pH in the environment where omeprazole is acting. The body has many different bodily fluids that have very carefully regulated pHs, okay? Now, that's done through something that is called a buffer. A buffer solution is a system of an acid and a base, okay, that together will neutralize, all right, or will limit the pH change that takes place when you add more acid or more base of a different acid or of a different base, all right? So in reality, we always look at a conjugate pair. Remember, we talked about conjugate pairs when we talked about acid and bases, okay? We're going to have a weak acid and its conjugate base, or a weak base and its conjugate acid, okay? And by equilibrium, through Le Chatelier's principle, that they will react with added acid or with added base in order to neutralize them and keep the pH from changing significantly. All right. Now, this can get a little bit more complicated, and I have a whole other video, and I'll show you that in the next page, that goes through many pages of how buffers work. All right. But this is not something that SL is required to know. If you are interested, I have the link, so don't worry about that. But you will need to be able to calculate the pH of a buffer. All right. The easiest way to calculate the pH of a buffer is using the Henderson-Hasselbalch equation. All right. pH is going to be equal to the pKa, so that is the negative logarithm of the acid dissociation constant for the main acid, plus the logarithm of the concentration of the base, of the conjugate base, over the concentration of the acid. It's a very straightforward idea. So here, let me show you on this example how to calculate the pH of a buffer. Okay, so if we have a particular buffer that happens to be composed of half molar ethanoic acid and 0.75 molar sodium ethanoate, right? We have our acid, we have the concentration of our acid, so we got our HA, and we got the sodium ethanoate. The sodium is just a spectator ion, so we do not need to worry about sodium itself. We only worry about the ethanoate. And the ethanoate, we have the concentration of that, so all we need to do is place this into the proper places. The base goes on the top, the acid goes on the bottom, and when we calculate the logarithm base 10 of this fraction, and we add it to 4.75, we get that the pH of this particular mixture is going to be 4.94. All right, so that pH is going to stay relatively close to that value when you add small amounts of hydrochloric acid, when you add small amounts of sodium hydroxide or any other substances. So this is highly important for our body. Our blood requires to be very tightly buffered and for the pH to change very little, because otherwise it would affect the capacity to carry oxygen, to carry carbon dioxide, And clearly, carbon dioxide dissolved in water is acidic. So it's important that we do not acidify our blood. Okay? That's why we have a buffer system in our blood. Okay? And many drugs, obviously, are going to have different function depending on their pH that they're going to be there. If you want to know more about buffers, all right, I'm not going to go through the whole thing, but just find this link, all right, and go to it, or just search through my other links in this page. All right, thank you. This is it for pH regulation.